Good afternoon, ladies and gentlemen. Welcome to the season of the CBS. I'm Jia Kang, and I will be chairing this afternoon seasons. It's an honor to have the distinguished Professor Chao Peng from Peking University to deliver his speech. And Professor Chao will have approximately 60 minutes for his talk and followed by a 5 minutes QA sections. Now let's welcome Professor Peng.
Okay. Thank you so much for the introduction. Today, my talk is about some combined field for the mathematics and the physics and also engineering. And we try to use some kind of concept of topology to the engineering problem, that is to control the direction of the net emission, and we call it unidirectional net emission. So this is a very important feature in the engineering field, and we want to use it to improve our devices toward a large volume of data communication and a lot of different purposes. So today, my talk is about firstly, I will introduce some general principles about how we apply the concept of topology, which is a mathematical concept, to the area of the photonics. And I will introduce some particular concept called topological charge. And we can use this concept to, to depict the behavior of the radiation, which is critical in the photonics domain, that we can use it for energy transport or manipulation. So the second, I will use this concept of topological charge to show that some consequences. By applying this topological concept, we can make several important features. Particularly today, I will focus on the unidirectional radiation. We call it UGRs. I will give more details later. And then I can introduce some kind of mechanism in this physics, how it is behaving like this. And the third part, I'm going to introduce some kind of applications towards the reliability. And we want to use this kind of feature to improve the functionality and the performance in photonic integration. And finally, I will give some summary. So the story is start from the topic called photonic integration. That is saying that today we are trying to make a lot of data in computing, and also we want to make the big model, language model to do the artificial intelligence. So beyond this kind of purpose, we want to increase the performance of computation. And in the hardware aspect, we found that the Moore's law of the semiconductor industry is going to meet some serious challenges. That's most because when we shrink the size to small and smaller volume, it is very difficult to get it together, to get low power consumption and get a very high volume of communication density and several different purposes. So it opened a new opportunity that use photonics instead of electronics to do the purpose. As light is a particular basic particle that a human can manage it. And because light didn't have any mass, so when it's transported in the circuit, it doesn't cause Ohm loss like electronic link. So by using this kind of technology, we can combine the photonics with the well-developed semiconductor industry called silicon industry. So we can put it light, transport, and then manipulate it on the silicon platform. That's called silicon photonics. So if we can use this kind of technology, we can use optical link instead of electrical link. So that can possibly make more faster and much faster and much energy efficient link towards a different purposes in the information transportation. So what we want to do is actually we have decades of effort to do this photonic integration. And from the very beginning, we are trying to do the optical interconnect, just like a pluggable, we call it pluggable optics. That means we can put different modules on the circuit board, and then we can put a circuit like a CPU or GPU on the board in the center, and then we can use optic link like a plug module near the CPU but on the board. So when the time goes, we can see that we are trying to increase the density and the connection bandwidth by different technologies. So from very beginning, the general one is pluggable optics, and later we have generation two, we call onboard optics, and then 2.5D co-packaged optics and the 3D co-packaged optics. And nowadays, we are towards the 5th generation, we call the 3D co-package with integrated laser. That means we want to put the laser and the optic link together on the board. So laser is very important. We ask for a efficient and compact on-chip laser. It can be very small, very efficient, and can integrate on the circuit, on the CPU or the circuit. So, but it's very challenging. That's because when we do the photonic integration, particularly in silicon photonics, we know that the silicon material is not favorable for light emission because the silicon material cannot directly get transition to create any light emission. So in that way, we need to add a different material on the system. For example, with 3-5 material, it's bilateral, have light emission. But this is still very challenging. That's called the laser on the chip is a very challenging task for the photonic integration. So another task was challenging on the optic link. We call it losses. Losses is very important because you cannot put laser on the board. So you have to external laser, use different material. So when you go the light into the photonic chip, you definitely need a I/O port. We call it a grating coupler to channeling the light from outside the chip to the on the chip. So at this interface, you need a very power efficient input and output port to make the light go through this. But light is very different from the current because light cannot easily bending or guiding because it's a wave. It's not just like a current. It can go use metal to guiding it. So basically, when you get light onto the chip, you want to build the whole complete optic link. You still need a further different kind of component, and we call this is the very standard or typical communication link. You need to have a modulator to put your data or signal onto the light, and you need to propagate it on the chip. We call it a waveguide. And then when you use this light to different purpose, you probably need to go the light out of the chip and to get another chip and finally get a detector to receive the signal. So when you call the whole link, we call it optical interconnect. And you can count the loss, how much loss on this link, and you can count loss in different modules. And we're saying the coupling loss is typically 5 dB, and the absorption is like 7 or scattering like 3 or whatever. And then when you count all the loss together, you find that the typical optic link will get a total loss of 20 dB. That's what means. That means we considering a typical laser can have an output power like 0 dBm or say 10 dBm, depends on your technology. But once you have so large power consumption in this whole link, that means you can hardly get sufficient enough energy in the detector. So the whole link can be very not efficient and they can even not work. So that is why we are paying so much attention on the loss on the link. That means if we can lower the loss on every component, that we can use it for the optic link. So topology can help us to get this goal. And the topology is actually a mathematical concept. So when we combine it in the physics, particularly in the photonics, we get a different region called topological photonics. It's basically, we can say that the photonic system is concentrated on the solution of Maxwell equation. So Maxwell equation can get a mathematical structure. So if you can find some kind of invariance, like the geometry property of the parameter space, you can use the protection of the invariant in this parameter space to protecting some target property of the photonics from the perspective of photonics. And some of the property can be used to improve the performance of the photonic device. That is the philosophy of photonic, topological photonics. So in the region of photonic photonics, the most popular, or say, intensely investigated devices called waveguide and lasers. This is two typical devices we pay a lot of attention. So first, waveguide. That is very simple. You need the opt link to be very low loss. So you probably need to make the light very robustly propagating on the chip. So the topology can help on this because when the waveguide is protected by some kind of trend number, you can make it unidirectional propagating in one direction without or immune to the backscattering. That means energy can propagating without loss. So people pay a lot of attention on the waveguide. Other part is the laser. Just as I mentioned, the laser is very important to the optic link. So is there any way to make the laser more stable? Is also a very important topic. So also, we can use different topological variants like chain number, spin chain number, or valley chain number, different chain numbers. That is some definition in the primary space of Maxwell equation bound structure. So when you use this kind of property to protect the lasing behavior of lasers, you get a robust laser with respect to the random disorder or something else that you can make it more stable in the industry. So this is also a concentrated area to do it. But what I was doing on pay a lot of attention to is a different kind of topology variant. We call it topological charge. Actually, topological charge is a very simple concept to reflect how the radiation behaviors in the primary space. Just as I mentioned, that an optic link become very lossy, and it will be hiding the functionality of optic interconnection. So we can ask where the light goes. Actually, the light cannot be, some of them will be absorbed by the material, but most of them is gathering or radiate to the free space. That creates loss. So if we can answer how the light go out of the system to the free space, that means we can handle or we'll say in suppressing or eliminating the radiation, that we can lower the loss. So this is a very complex problem because once you can solve, you want to solve how the light is escaping from a system, you need to solve the four-wave Maxwell equation to see how much energy is radiated towards to the infinite. But it's very complex because you're involving a lot of parameters and a lot of geometry of the real space, geometry of the structure, and very difficult. So is it any simple way to understanding what is the how to make the radiation disappear is what we can do. So we define a concept called topological charge. It's very simple. Actually, when we can see a light go out of the slab or say the system to the free space, we can always define a polarization of the light. Light is always polarized because light is a transverse wave, so you can have the electric field direction to define as the polarization of the light. But light always have polarization because it always have electric field. If not, it's not a light. So once you have this polarization, you can find the major axis of the polarization ellipse. So that means we can use a vector to represent the direction of polarization. So the topological charge is actually a very simple, a 1D number of polarization vector in the momental space. So what it means that you can see like this way. You can find the momental space like Kx, Ky is a two-dimensional brane zone. So in each point, you can define the polarization of light like a vector. So if you find a vortex in this momental space, that means in the vortex center, the polarization is ill-defined. You cannot define any polarization. A simple example is just you say your hair wing. You can see a hair wing. Your hair wing, you cannot see any hair on that. So this is very in the center. You cannot see the polarization. So once the polarization is not defined here, that means light cannot radiate here because it cannot gain appropriate polarization. So here just means the radiation vanish. That is what we found. So if it gave us a very simple picture. If you find a vortex here, the vortex center point is where the radiation disappear. That is what we want because we want to eliminate the radiation. You don't need to calculate sophisticated equations in Maxwell equations, but you just simply find the vortex. That's enough. So we call this 1D number as topological charge. Okay, by using this concept, we can use this very simple concept to make the radiation be controlled. That means you don't need to solve the four-wave matrix equation. You just need to find the vortex in the moment space. So here I will introduce two theory consequences by using this picture. Actually, we have another work on this kind of concept because it gives us a simple way to represent how radiation behaves in the world. So we have different topics. So we can actually put different charges together to get a better confinement of light. And we call it a merging BIC. BIC means bound state in continuous. It's a concept of physics, saying that a state is allowed to radiate, but indeed it doesn't radiate. So in the other concept, we can manipulate the charges to put together to forbid its radiation even it is allowed to radiate. So we call it a high Q cavity. We call it a topological Roberts trapping of light. This is one part of our work. We published some paper in the 3 years ago. But what we are going to do today is we introduce this part, and we want to find a different way is we make the charge, like topological charge, on one side of the device. So we can make it unidirectionally radiate to the direction we want, but forbidden radiation we didn't want. So we call it unidirectional guide resonance. And also we give several consequences. So today I will focus on the second part of the consequence of the charge manipulation. So we back to the motivation. So why we needed to a unidirectional radiation? So we put a device here. It's a very simple greeting. That means a geometry is periodically repeat itself and form a periodic structure in real space. So this device is usually used as the optic ports to make the light go out of the chip or according to a time reversal symmetry from outside the chip to the chip. This is two directions. So why is it so important? As I mentioned, the optic port have very large loss to make the optic connect not work. So how is loss happened? We can see when a light is traveling in this way, it's intended to go out to couple to another device. But when you see the structure is almost up-down symmetric. So that means if the light can go upward, it for sure can go downward because it's symmetric. So you are receiving device is always on the surface of the device. You can hardly put a device on the button because it's a button, right? It's a chip substrate. You cannot put different things there. So that means this energy is totally at waste. You cannot use it. So that means half of the energy is waste. That means a huge waste of energy in optic lens. So our question is, can we make a design to make the light go upward but not go downward? That is our purpose. If we can do this, we can do a very high performance optical or I/O or optical ports to make the system more better to be energy efficient. So from the max equation, of course, it's possible. You can solve the max equation to create a different kind of waves and go an interference upward and downward. We get a destructive interference in the downward and a constructive interference upward. That's what we can make it. So it seems reasonable, but it's difficult because you need to tune another parameters and don't know how to tune it. So by using our charge picture, it will become very simple. That means we start from a symmetric structure. The up and the down is the same. Of course, the radiation in up and in down is the same. And in this way, you can find a condition that is both the upside and downside of radiation is destructive interference. That means it didn't radiate. So in the charge picture, that means you can find a vortex in both upward and downward. You have a single integral charge vortex in the upward and downward. So further, you can break the symmetry. You make the grating, or say the periodic structure, and symmetric respect to Z. So in this way, that means the up and down is different. You can find a different radiation property up and down. So of course, when you see the charge picture, you can simply find the charge of integral charge will split to two half charge. Okay, and then further, you can continue to break the symmetry, get stronger, and the upward and the downward become more different. So in some case, you can make the half charge be merged again in one side, but keep the depart in the other side. This is reasonable, right? Because up and down is different. You have a chance to make these two merge in the upside, in the downside, and then keep it in the upside. So in this way, we can do it. So we find the resonance we want. It's only radiated to upside and it's not downward radiative. So very simple. And you don't need any mirror in the downward. You don't need any mirror in the bottom to prevent the light go this way. You just nothing happen here. Just this geometry to make the light unidirectional to one side. Okay, that is very simple. So our philosophy, you can easy to do it. So we make an experiment. So we fabricate sample and we see, okay, this is top surface. We observe it. It's bottom surface. And this is the far field mirror image. Seeing that, you can see the momentum space. So what we concern is a Y point, and also here. You can see that here is bright. That means light can radiate from upside. But here is the downside is always dark. That light is not happening here. So when we see in this kind of the spectrum, also from the upside, you can always observe a very beautiful Lorentz line shape. This is a distinctive feature of the resonance. But on the downside, you can hardly see any resonance. And here is the optimal point. You can see a little bit very small resonance. That means most of the energy is forbidden in the downside. So if we measure the charge evolution, that is what happened. And it's split and merging in some place. And we can measure it in the experiment to find where the charge is. And here, the cross point of the two different half charge is exactly what we want. The animation of the emerging of the unidirectional resonance. And further, we can measure some performance characteristics. So the resonance and the Q and the different aspect ratio, we can find it's equivalent to say that 99.8% of energy is go one side. This is very high efficient unidirectional radiation. And you can also see that the wavelength about almost 30 nanometer bandwidth, you can get a very pretty nice the directionality. And also the angle tolerance is pretty good too. So this is also this work tells us that we can indeed give a example by using this topological concept. We can make the directional radiation without jumping or diving into the complexity of Maxwell equation. It's a simple mathematical concept to use in photonics. So in physics, we want to understand what happened, why this becoming happened, and everything is from Maxwell equation. Okay, so no surprisingly, we should be understanding the phenomenon in this Maxwell equation. So how this kind of phenomenon comes? We say that the physical origin is called interbond coupling. That means if we find a periodic structure, we can get a unit cell geometry to break symmetry in z direction or also implant direction, depends what you want. And you can make two energy bond or photonic bond to couple together. So from we count the degree of freedom, we can find a Hamiltonian to describe system. That means in the unperturbed system, you get our energy 1 and energy 2 is diagonal, right? They are not coupling from this. So when you break the symmetry, we introduce the off-diagonal terms to make them couple together. So when we see the system, we can solve this matrix with, we can find this actually describe the mode hybridization of the two bond, this guy and this guy. So if we see from the polarization, we can see the radiation polarization is also a hybridization of the radiation of the two eigenstate. So we count the degree of freedom. We can see that this bond and this bond is two different bonds. It's different, right? So this guy and this guy too are also linear independent. So that means their linear independent combination can make any polarization you want because you have 2 degree freedom to construct the arbitrary polarization you want, including what we want the EL-defined polarization, the singularity. So from this way, we in principle understand it's possible And also, it is not easy to constructing it because it's arbitrary. You don't know how to mix it to get your purpose, but it tells you you can do it. So if you from back to the charge picture, that means we can see the charge, that's the Wendy number of the topological environment, is actually very robust. It's actually robust in the momental space. It's a conservation, it's a conserved quantity in the momental space. From mathematical reason, it's just like a Stokes law in the continuous system. So we can count, we can forget the different sophisticated geometry. We can focus on the charge. Thus, we can do a very simple math. If we want a vortex, say charge equals 1, so we can use the Briggs symmetry to get it to 1 equals half plus half. So you got a half. When you continue to tune the parameter, you can have some half merged together to get a unidirectionality. But we can ask the premise of this realization depends on you first find A1, and it looks very weird. You need to construct a charge equals 1 first, and then you can get a unidirectional. So this maybe make this phenomenon is very difficult to find. But the fact is not this. Because we have an interbond coupling, you can make it from nothing. You can start from 0, get minus half plus half mass, half plus minus half to positive half, still obeys the conservation. So that you can split the half charge from nothing happen here, and you can also construct the half charge, and then you have a chance to make a half the positive half to another positive half to get an integer 1. So it also works. So in this way, we can freely to construct the unidirectional radiation in different configurations. It's very common and general in photonic system because the interbond coupling is a very general phenomenon in photonic system. So we can track it in different parameter evaluation. So when we check this charge and we can tune the parameters, we can see that it's continually evolving in the whole brain zone, and we can track it by you want. And you can also cross the net line and to get the near field. It also works. So that means that it's really a conserved quantity in the whole brain zone. So if we count what really happened here, we can give a very straightforward picture, like a close of wrinkles. So when you get a close, and the polarization is just some wrinkles on the close. So that means you get a wrinkles up, and you always get a wrinkles down because you straight the close be flat, all the wrinkles should be disappear. So actually polarization is a geometry property of the winding of wrinkles on the parameter space. So it's a conserved quality. So this is the mathematical fundamentals of the phenomenon. Okay, so here is the fundamentals. So from now, we see the physics and we see its mathematics. And the next step, we try to make it some engineering purposes. And then we try to find some application by using this kind of unidirectional radiation to see what we can do. The first thing is that we call this the UGRs. We call it unidirectional Gardner resonances. In general, we don't need to require any symmetry to realize the unidirectional emission. You can arbitrary break symmetry to construct this if you can merge into half charge together. But you can still own symmetries. For example, you can preserve the C2 or P symmetry to make it happen in this system. So what's the difference? So when we see a resonance system, when user light to excite it, we generally have 4 ports and 2 resonance to get involved in the system. There's K and minus K and get 1, 2, 3, 4 port. So when you get the UGR together, actually you can have a response of this. When you apply the symmetry on this, the port can be selectively closed, like 1, 2, 3, 4. If 1 is UGR, that means this port is disappeared because the charge can close it. So we can make the 4 port to like 2 port. And also, when the system is symmetric, that means this guy and this guy, like this, for this example, this is a P symmetry. This guy and this guy should be the same. This guy and this guy should be the same. So the 4 port can be set to 2 groups, and in each group they're the same. So that means we can, and this guy is disappeared we just get an equivalent one-part model. And also similar to this, we have a C2Z symmetry. You can also reduce the 4-part to the 1-part model. So what is that the concept is to reduce the independent part? This is because we can have a very interesting phenomenon by using this kind of 1-part model. So think about a tank. You have a water flow in and a water flow out. So when you get 1 part in and 1 part out, you can always, if it's a harmony constant, the flow in should be always flow out. Otherwise, the tank will be filled or depleted, right? So this is the equivalent to saying that the input and the output intensity is the same. So we're back to the photonics. That we can say a input you get to the system, part of the light will get in the resonance, excited resonance, and some of the light will not excited resonance directly reflect or transmitted. And the resonance is going to emit the light out because the system has only one port, so the light can go the same way back to the input. So when you combine this direct transmit or reflection plus the radiation, we are always the same from intensity from the input. So that means this is the all-pass filtering. It's all-pass. That's everything is go in and go out. But it's just all-pass. What happens in this system is not purely an intensity environment. That means still some of the light is going into the system, walk around, and go out. So it will bring actual phase. So from the intensity, you can see the input and output is the same. But from the phase, depends the resonance, how much getting the resonance, it have a phase difference. So we call it all pass, but phase shifting. This is a very important phenomenon. So when we back to optics, what happened in this optics? We can build this kind of interesting unidirectional radiation. So from this kind of C2 symmetry, we can have a light go here. It's like a perfect mirror. No light will be linked to the button, and it's perfectly reflect with kind of phase shifting. So if we have a p-symmetric UGR, we get a perfectly passing through surface. It can directly pass through this kind of surface without any reflection, but also it will give an actual phase. So this actual phase can also use to do the phase modulation. That means we can use it for LiDAR, and with like a optical phase array, you can put a light on it, and we get a different resonance. It's on or off. Give a different phase. When you connect different phases together, you have a directional scanning or spear steering of the system. So this can be solved use a very standard TCMT model in the photonics domain, but I'm not going to introduce the details. But you can see that in one part, it's have a phase response. In the other direction, you don't have any response, just like this. So we have some kind of calculation to see what happened in the real structure, and we make this phenomenon. We can see this. This is a device we fabricate, and we can see that from transmission, we can see this is a ring of Newton ring, the feature of the interference. And here, the ring is from dark. When you scan in the wavelengths, it's from dark to bright to dark, seeing that the phase response. But you see the reflection drawing the same range of the wavelength scanning is always dark, such no phase responses. Okay, so use this very interesting and important unidirectional resonance. You can make this kind of mirror to do different purposes. A second one is also important. That's our original motivation. We try to make the optical I/O more power efficient, right? We want to eliminate the light, go downward to make the optical power concentrate in upward and make the optic link more power efficient. So we can do it without mirror on the bottom to promote the power efficiency. But here we need to think about the reliability to get compatible with the semiconductor industry to make some kind of how to say appropriate geometry, make it compatible with the fabrication process. In previous, we say that it's a sliding or a tilted etching geometry. It's difficult to make. But here we get a different kind of shape. We say it's L shape. It's very simple. We fabricate or in the silicon photonics foundry. So we back to our charge picture. What we want is pitting here. We can make a -1 charge split to 2 minus half, and by tuning the geometry of L shape, we can get one side is back to -1, and the other side is still depart. So in this way, we get the unidirectional guidance like this. We can still have no mirror in the button, and it's ready on the surface. So further, we want to make it a real device. How this is the uniform direction region, we want to connect to a tapered waveguide to on-chip propagating. And the drawings process, we need to do some kind of trick saying that we meant to calculate the bound dispersion to match the graph velocity, match the momentum in a different way. So we get a optimization region to get a continuous change of shapes to make this transition. So from the simulation, we can see that if we put a light input here, we can unidirectionally radiate to the outward, but not much light is going downward. That is the device we designed. And this way, here, we already consider it. This is a real device. And also, we want to connect this to a, a real fiber that is a receiver. So we use a industry, it's common use, say, in calling SMF 38E plus fiber. This is a very famous company to make a single mode fiber. SMF stands for single mode fiber. This is a very standard fiber used in the fiber industry. So we can match the model volume. I would say the MFD, the mode field diameter, is like 10.4 micrometer, and make it the position and angle be matched with the fiber. This can be done by tuning the optimization region to get it fit onto the fiber. So we can calculate the efficiency of coupling. We can see in much region of angle and wavelength, we can make the coupling efficiency better than 1 dB. Okay, the next part we can try to make it. So we can use a very standard the fabrication process like EBL and ICP to do two-level overlayer etching and to get the L-shaped the unit cell geometry, and we get a taping region and get the vibrating region, and we make the devices. Let's see what happened in the test. So this is the test diagram of our system. We say that we have a laser, we get a polarization controller, and shine the light on the chip. And the chip, the green light will go like this way and back to the free space, received by the photon detector. So this is the typical optical link used in the photonics integration. So we can count the fiber to detector inside loss, saying from here to here. This is the fiber, this is the detector. So the total optical link inside loss is just 1.24 dB. Think about it. It's in typical way, we have two green coupler. Recall that a typical green coupler have a 5 dB inside loss. So if it's 5 and 5, the waveguide will get 1. So it should be 12 minus 12 dB inside loss. But here what we done is only just about 1. So it's a much improved. And the second, we can also to calibrate this port and this port, how much is spent on this and this. So this is the typical the performance to say coupler to fiber coupling efficiency. And we say this is just 0.434 dB. That means 92% of energy will effectively go to the chip. 92% is not of energy. Most of the energy is go to the chip. And by using this trick, we can do different way toward a interesting way to do 3D stacked photonic chip. And we know that the circuit can be multi-layered, that we call PCB, right? We have different layers. We can put the device on this way and put the device on the bottom, and you can do interconnect in different layers. We have 6 layers or 20 layers for very complex way. But in photonics, it's very difficult. You just want to routing it in one layer. So what we can do is by using this kind of unidirectional, you can get a VIR, like a path, make the light traveling from different layers. For example, light can go downward. This is one layer, this is another layer. This spread in some kind of distance. So light can propagating and routing in this layer, And if its routing is too complex, you want to jump to another layer, you can use this unidirectional gradient coupler to go up there and then propagate. So this can be interlayer interconnection. So that means you can get a photonic circuit board, also PCB. So to do a different layer of interconnection. So let's see the performance. So by using this, because the light is unidirectional radiation, here is disappear, is disappear. So this way you can effectively transport it. So the total from here to here, the insert loss is just minus is smaller 1 dB. It's very small. So think about a conventional one. So this is a 5, this is a 5, so it's about 10. That means 2-layer overlayer is possible by using this kind of unidirectional radiation. That means you are possible to do 3D integration of photonics. So finally, I will just list several performance published or from the industry. That means we can say get a most efficient gradient coupler in our system, and by using topological concept, that 92% of energy will come to fiber chip. That really makes the system work. Okay, so that is pretty much to the ending of my talk. And I just introduced some kind of concept to combining the mathematical concept of topology to the physics and put forward to the requirement in the industry. So we say topological charge will brings real consequences in the world, and can use the substrate radiation to manipulate the scattering and to some direct emitting. So by using this kind of concept and technology, we can do a lot of way to improve the performance of photonic integration, and it's a very promising way to toward the different applications like the AIs and the computing and different ways. Okay, thanks to my collaborator, including my Professor Loda from Kyoto University, Professor Marin Sojazic from MIT, and different guys. And thank you so much. So thank you so much for this conference. And thanks.
Well, thank you for your wonderful talk. Now question time.
Okay.
I will have a little question for you.
Yeah.
This is a great talk, and I have learned a lot from the. You use some simple geometry and topological, and to create something more efficient. And I have a naive question.
Yeah.
Okay, I'm not familiar with the topic, so whether these chips in the future can be designed as a 3D.
Yes, it's a very good, actually very good question. And today, the industry of the IC industry is trying to have a different way to make the chip more powerful. So one is we call it advanced process. That means we have a 7 nanometer with a 3 nanometer or go further and further. But this way will be more and more challenging because pretty much close approach to the limit. So today, even in the semiconductor of the high-performance IC, the packaging, that's 3D stacking, will be very important topic for them. So not only the photonics and also the electronic chip, we're trying to do 3D integration. So here is also a way, when you do the electron chip in 3D, you pretty much need to do electric signal from layer to layer. So in that way, you also, of course, you can do the copper as before, but when you go faster and faster, it will be more and more difficult because you think about it, it's a very faster electron wave oscillation there. It's not like a waveguide, it's like antenna. It's radiate the waves everywhere. So if you want to eliminate the radiation, you need a more compact or short wavelength wave to do it. That is optics. So that is from the requirement, we are trying to do 3D stacking of the optics to really into the chip. So still, from technology, we think it's possible, and maybe 10 years, you can see something happened in this world. Yeah.
Thank you.
Thank you.
Professor.